do get bored. Okay, so let me just get my mind back into, okay, so welcome now to lecture 11. You see, I haven't had to change the title. We're still working through chapter 6. We're still working through period doubling bifurcations, but let me show you there's a new chapter now out, and I don't know whether we'll reach it today, but if you access the Moodle notes, you'll see there is now the chapter 7. So this will be the next chapter that we're going to hit probably on Friday. But you should be able to do the complete problem set. So this is problem set number 3, and for this week's problem set, I definitely took it back a little bit. This used to be problem set number 2, but just because of the pace that we're going through, I shifted it to problem set number 3. So this problem set will just work you through the very last elements of these 2 local analysis chapters on bifurcations. And yeah, we're going to continue on with chapter number 6, so the period doubling bifurcation. So just to review, last time we did the local analysis. We did the dominant balance. This is for the case where the derivative of the function fx at 0, 0 is -1. We found, and then we analyze these 2 fixed points. Sorry, not the 2 fixed points. These are two cycles. And then we started our examination of this toy example of the supercritical period doubling bifurcation. And I said this is going to be what we're going to start off with today on the Wednesday class. And we won't go through the subcritical example, but it's very, very similar to the supercritical. And you can also see in the notes that it's done pretty quickly. Okay. Can I drop a link to the notes in this? Yes, I can. Well, you're being a bit lazy. Because it'll probably be faster for you to access it, but let's see if I can do it for you. So this is the 21st entry. And then if I copy this here, drop it into the chat. Okay. All right. So we want to look at the canonical example. Of a period doubling bifurcation. And this is a supercritical P2 orbit. So in this case, your F is going to be a cubic equation of 1 plus mu times x minus x cubed. Okay, so let's just do all the usual steps. We're going to find the fixed points, then we're going to check their stability, and that's basically it. Let's go. So firstly, fixed points. So let's go and solve x equal to f of x. So we've got x is equal to x plus, sorry, that's a minus x minus mu times x minus x cubed. So x is equal to 0, or looks like we've got, move this over, we have a 2 is equal to minus mu minus x squared. Move the mu over, or move the x over, and then solve for that. So you have x equal to plus or minus root of minus mu plus 2, like that. Have I done that right? I've moved that over. Have I done that right? Minus mu, I have a minus x here. I move that over to the other side. That becomes a 2x. You cancel the x's. U here. Okay. That looks about right. Okay, so I need mu plus 2 to be negative. So for this thing here, I need mu plus 2 to be less than 0, so mu must be less than minus 2. Oh, I know what I did wrong. I was confused. This is a plus, and then this is a plus here, and then this is a plus here, and then it moves over to the other side, that's a plus here, and then this is the other way around. Okay. So this guy exists for all mu, and then this guy only exists for mu greater than minus 2. Okay, now you go and you get your stability, so let's do that. So check stability. And let's take our derivative, fx. So that's a minus 1 plus mu plus a 3x squared. And then you have to check stability at all these 3 points. Let me call this one here x plus minus, just for the notation's sake, and then this one just be the origin. So firstly, fx at 0 is equal to minus 1 plus mu okay, and just for my sake, because I'm slow, that's minus 1 minus mu. So if mu is negative, you're adding to this one, and it becomes more stable because it becomes less greater than minus 1. On the other hand, if mu is positive, then you're subtracting from minus 1, and it becomes unstable. Right, so you've concluded from this, x equal to 0 is, so if mu is less than 0, it's stable. Since this quantity here will be greater than minus 1. Let me get both sides of it. So actually, let's do this one systematically. So let's do this one systematically. So you need to check. So you need to check where this magnitude here is less than 1. So when you check that, you just have to check whether it's less than 1 or greater than minus 1. So note that fx at 0 is equal to minus 1 if mu is equal to 0. Okay, and then note that fx of 0 is equal to 1 if mu is equal to minus 2. Okay. And then after you've done that, you just kind of check on each subinterval where it is. So let me make a little graph here. So this is minus 2, this is minus 1, this is 0, this is 1, and so forth. So if mu is extremely negative, if mu is extremely, let's say mu is extremely positive, then this guy will be negative, and that will be unstable. So it changes here. So on the right here, it's unstable. So if you put in mu, for example, is equal to 10, then you get minus 11. And it will change on the other side, so this is stable here. And then it also changes at the value of minus 2. So on this side here, it should be unstable. Yeah, because if mu is, again, if mu is extremely negative, then you're adding to this quantity here. It's minus 1 plus a big number. And then this will take you on the other side of this quantity thing. So this is fx greater than 1. This is fx between minus 1 and 1. And then this is fx less than minus 1. one way that you can do this kind of analysis. You just find the critical points where it passes through -1 and 1, and then on each of the subintervals, you just either draw a graph or just figure it out based on putting in numbers. Okay? All right. So I will erase this bit here. Erase this bit here. And then just put it into, so therefore, x equal to 0 is, it's a lot easier to do it in a graphical form like that, but anyways, this is -2. So it's unstable if mu is less than -2. It's stable if mu is between -2 and I think it was 0. And it's unstable if mu is greater than 0. Okay, and then you have to do the same thing with these other two guys here. So let's check fx at x plus or minus. So you put this quantity into this thing here, so you have to square it. So it's going to be a -1 plus mu plus 3 times this quantity squared. And I think that's right. Oh, sorry, it's mu plus 2. Bit too hopeful there. Mu plus 2. All right, so what do we have? We've got a -1 plus a 6. That's 5, I think. And then I've got a minus mu plus a 3 mu, so that looks like a 2 mu. Okay, and then again, you just check when that is between -1 and 1. So fx of x plus or minus is equal to 1 if 5 plus 2 mu is equal to 1. So that tells you that mu is equal to what? 1 minus 5 is -4, then -4 over 2 is a -2, I think. Okay, if mu is equal to -2, and fx of x plus or minus is equal to -1 if this is now -1, the 5 brings over to the other side, that's a -6. So you get mu is equal to -3, I think. Yeah? I think so. -3, 2, 6, -6. Yeah, okay. Now, this one here you don't have to worry about because it's outside the range where it exists. And so you only have to worry about this quantity here, and then you just have to worry what happens on the left and what happens on the right. Okay, so again, you can draw your little diagram here. So like that. There's a -2 here. Now on the right here, if mu has very, very positive numbers, this will be a large quantity, and so this will be greater than 1. So it's got to be unstable out here, and it's got to be stable in here. But it doesn't exist in this region. Okay? The other way to do this, by the way, some people prefer to, when you work with these inequalities, that sometimes you'll just do it from both sides like this. And then you solve the equation from both sides. You move the 5 over on both sides. So this becomes a -6. 1 minus 5 is a -4. And then you divide out. So that's a -3 over mu over -2. Yeah. Okay, but this one here is it exists in a region, so this condition is superseded by this condition, which tells you that the fixed point doesn't exist in the backwards region. That's actually a faster way of doing it, isn't it? And then just make sure that if you do have a minus sign, then the less than signs have to swap if you divide out by a -1. I should have done it that way for all the other problems, really. Okay, so in conclusion, we've concluded that therefore x equal to x plus or minus is unstable if mu is greater than -2 and it does not exist if mu is less than -2. All right. Okay, and then you summarize this. You summarize all of this with a diagram. And when we do this diagram, you'll kind of see why there has to be this period doubling orbit, or you see a hint of why there might be a period doubling orbit. Okay, so step 1 is you do the fixed points. Step 2, you find their stability. Step 3, you find the ranges for the stability. Step 4, let's just draw our bifurcation diagram. So far we've concluded that you've got 2 fixed points, and I stupidly forgot to write down the equation for this. It was plus or minus root of mu plus 2, I think. Okay. So what does it look like? Well, so firstly, okay, 0 is stable in the central region, unstable outside of those 2 regions, and you have the 2 critical points. I better do my line first, and then I'll have to make it dashed afterwards. So that's -3, that's -2, that's -1, that's 0, that's 1, 2, and so forth. Okay. It's unstable for this region, everything to the left of this, so let's erase that. And we'll make it dashed. It's stable within the band from -2 to 0, and it's unstable outside of that band like this. Okay? So x equal to 0 is a fixed point. Now, on the other hand, you've got these 2 arms that are coming out. You've got x plus and x minus, and you know that they look like square root arms, right? And they're coming out from the 2 here. The other thing you know is that where they come out, it's unstable, so it should be dashed. So you can have one unstable branch like that. So this is x plus. That's root of mu plus 2. And then you have the other unstable branch like that. That's x minus. That's minus root of mu plus 2. Okay? Having done that, you can see that this has to be a pitchfork bifurcation. There's your pitchfork. And you also know that it's subcritical. Subcritical, as I said, the memory device I use is sub is kind of bad. You got 2 unstable arms to 1 stable arm. So this guy here is a subcritical pitchfork PF. Now, that's all fine and good, but the interesting region happens right here, you see. So notice that it's unstable from this central curve, and it's also unstable from these 2 ones. So if I were to start at a point, say, located slightly off from the 0 solution, you know that you always have to move away from it. You can't move towards it because it's got to be unstable. And similarly, you know that you have to move away from this top one as well. And similarly, you have to move away here and move away here. And so that forms the natural question of where the system has to approach. It can't approach a fixed point. It can't approach a stable, a fixed point between these 2 curves because you know that doesn't exist because you've already solved the equation x equal to f of x. But it has to approach something, or at least it seems it has to approach something. So that's why you're led to the intuition that it's flipping back and forth between 2 points, between these 2 sets of dashed lines. And so that tells you that, oh, perhaps there is the existence of a P2 orbit in this region for x greater than 0. Okay? Let's try to, I think the next step was just doing some cobweb diagrams to figure out where that might exist. Actually, let me write the conclusion at the top here. So we conclude that for x greater than 0, rather we can conjecture for x greater than 0. Let's say conjecture rather than conclude. Conclude is too strong of a word. We conjecture the existence of a P2 orbit. Right? For the same rationale as I said before, the system has to, between these two, in this narrow band and in this band, you'd expect there to be some kind of steady state of the system. That's a very interesting question. You expect there to be a steady state of the system, and you know it can't be a fixed point, so perhaps it's a P2 orbit. So now the question is, I mean, this is all very interesting science, right? How do you come to some conclusion? The Rebrac 20 has asked, could it not just be the case that our assumptions are wrong? That's very true. So, but what assumptions have we applied in this case? So the only thing we've done is we've solved for the fixed points. We haven't done any approximation. This is not an approximate procedure that we've done before. We've only found our fixed points. And so I think the only assumption here is the one in which the assumption is, does it have to be the case that the system has to approach some kind of steady state? Okay. Now, if that assumption is true, that the system does have to approach some kind of steady state, then you would say, well, it can't be a fixed point. And so the natural extension of that is a cycle. It has to be a cycle. It has to go from, x1 to x2 back to x1. It might not be a 2 cycle. It might be a 3 cycle or a 5 cycle or a 10 cycle, but it perhaps is a cycle. And then if that assumption is wrong, then the question is, well, what does it have to? Then perhaps it might be that it doesn't approach any cycle at all. And that's kind of chaos, right? So so I think it's safe for us to tend towards two conclusions. The first conclusion is that it can't approach a fixed point, and therefore it might approach a periodic cycle, a 2 cycle, a 3 cycle, a 5 cycle. The other possibility is that it doesn't approach any cycle, and then it just stays quote unquote random for all time. And that's the interesting thing that we'll investigate in the future. Why couldn't it go off to infinity? That's another very interesting question. It can't go off to infinity because of the stability, right? So you know that if I start off from a point here, the path can't take you past the dashed line because you know that it can't approach the dashed line, right? And conceivably, you'd argue that it can't jump through the dashed line. It has to be a continuous line. It has to be a continuous curve. So you make the conjecture, you make the conjecture that the trajectory of the system can't cross dashed lines or solid lines. Now, why can't they cross dashed and solid lines? Oh, that's an even more interesting question. So suppose I had a system here, really taking us off track, but okay, here's the question I'll ask you. Okay, I've got a system in which I've got an unstable point here. I've got an unstable one here. There's x plus, there's x equal to 0. And my claim to you is that the trajectory can't cross. It can't do that. Lots of interesting questions. Why can't it do that? Why can't you have a crossing in that fashion? This goes back to existence and uniqueness, right? You would make the argument that if you have a crossing in this manner, then you have one solution which goes that way, and you have one solution that goes that way. And that can't be true, because what it would indicate, you have to think about that because we're not plotting it in the right space. What it would indicate is that at that point, you've got two different gradients. And if you have two different gradients, then your function is no longer single valued. The function f is no longer single valued. So for all functions you can think of, except for the non-pathological kinds, the ones that have singularities or they've got multiple branches, if you wrote down your f in that fashion, right, and this thing is nice and continuous and it's got smooth gradients and stuff, then this kind of thing can't happen. And this goes back to existence and uniqueness. If you've done some existence and uniqueness in your ODEs courses, basically, as long as your ODE is nice, you should have uniqueness, and you wouldn't have this kind of crossing. So you come to the conclusion that you always have to stay in that region there. You can't leave that region there, but you can jump in your orbits. When you're given a map, so another question here is when you're given a map, for example, on problem set 3, how do you know what type of bifurcation occurs? It depends on the context of the question. So if the question is asking you to draw a bunch of cobweb diagrams, then basically you draw the cobweb diagrams and based on what you see, you intuit what the bifurcation diagram has to look like, and then just like when we did it here, we said, oh, that guy looks like a pitchfork. Okay, that's one way of doing it. And again, it depends on what the question is asking you, what the assignment question or what the exam question is asking you. If the exam or assignment question is saying, do a bunch of cobweb diagrams, justify by cobweb diagrams, then you kind of do this analysis, make these pictures, and based on what you see from the cobweb diagrams and based on what you see from this analysis, you can figure out whether it looks like a pitchfork, it looks like transcritical, it looks like saddled node, etc. Now, on the other hand, if the question is saying, do a local analysis and prove it, then what you would have to do is you have to take the function f of x, and then you expand it into a series, and then you do a little local analysis near that point, just as we've been doing in the last 2 weeks, in the last week. You do a local analysis around that point, and then you show that locally the picture has to look like the pitchfork. That's the second way of doing it. The third way of doing it, which I rarely ask, but has appeared on your problem sets, is that you take the function f of x, you expand it into a series, and then you figure out what all the coefficients are, a0, a1, b0, b1, and then you go to your notes and you flip to them, and where it says pitchfork bifurcation occurs if a0 is 0 or 1, and you check all those conditions. And under that condition, under those conditions, that will verify that the local picture does look like a pitchfork. So there are different levels, different ways that you analyze it. Given a general map, there's no answer that I know of. I can't tell you, given a general f, how do you just look at that f and know that you're about to get those kind of things? It sort of depends on whether you can restrict the class of functions even greater than that. So for example, if you said, let's look at a typical quadratic map, or let's look at a typical cubic map. Can you tell me the exact conditions that you're going to have, that you have these bifurcation pictures, and what type of bifurcation pictures you have? You can probably do that. You can probably sit down and write out those exact conditions. But in general, it depends on the context of the question. It depends on the rigor that the question is asking you to justify a statement. Okay, so we conjecture that for x greater than 0, there exists the existence of a P2 orbit. And if we return to the Taylor series, we can check. So I'm going to do it in the very boring fashion here, that a0 is equal to -1, a1 is equal to 0, b0 is equal to 0, b1 is equal to -1, b2 is equal to 0. And the P2 orbit is x twiddles plus or minus root mu. Previous by Monday's lecture. So my point is that if you go to Monday's lecture and you look up our approximation of the P2 orbit, we had a formula for it. and you go to this function here, and you go and figure out what the Taylor series coefficients are, then you'll be able to verify that the formula gives you this approximation of the P2 orbit. I don't expect you to memorize any of this, by the way. You're not expected to memorize these conditions, and I think it's actually bad practice for you to memorize those conditions. Okay? As long as you understand how we got to this approximation by Monday's lecture. Okay, so you've come to the conclusion that you've got these two arms, and remember that this is just a local condition. Okay, so this is a local condition. Meaning that this is it's a tilde. This only applies near that point there, whereas these two conditions apply everywhere. Okay? So you've come to the conclusion that you have a root mu arm here, and you have a minus root mu arm here. And again, you label this guy here. This is a P2 orbit. Let's call it P2, and then we'll make a big box around it like that. Okay? Now, how do you get this approximation, or how do you get the P2 orbit? You basically got two ways of doing it. The first way is you can do this kind of Taylor series approximation, just like in the Monday lecture. You go and figure out what the right balance is. So we could have, if we wanted to, go and put in a x on the left-hand side here, and then solve. You essentially want to solve the equation x equal to f of x. So you take this right-hand side, you iterate it again under f, and then you go and balance all your terms, and if you do it just right and you check the local balance, it should give you that formula. So you could do it that way. Of course, you can just go in the notes and read off the coefficients and use the formula that you found before. That's the other way of doing it. Or you can try your best to actually solve that equation, x equal to, this is cut off from the video. This is x equal to f of x. You can try your best to solve that equation, and you've done that in the first two problem sets. So as long as the polynomial is not so bad, you can try to do that. But in this case, it might be pretty bad because it's an x cubed, and I think if you iterate that again, you get an x to the 6. Yeah, you get an x to the 6. 1, 2. Okay, I think what happens if you try to solve this equation is you get an x to the 6 polynomial. You know that this fixed point at x equal to 0, this one x plus and this one x minus will appear in that equation. That removes 3. I'm guessing the x equal to 0 is actually a double root of that equation. That's 4, leaving you with 2 roots to solve for, and those 2 roots would give you the exact solution of the P2 orbit. It might not actually be that bad. You can try doing it yourself. You have to deal with that 6th order polynomial. Okay, so let's write our little conclusion before we do the cobweb diagram, and that basically takes us to the end of the lecture, really. Never seems like we have that much time. So we found that for u greater than 0, the system has 2 points. P2 points, x twiddles plus or minus root mu, which corresponds, which apparently, I'm going to say apparently because we've not proven it, corresponds to a stable P2 orbit. Right, so it goes from x plus, I shouldn't call it x plus because I've called the other one x plus, but it goes from, let me call this one plus or minus with the top there. It goes from x plus here to x minus and then back to x plus. Now, here I said we have apparently shown that because we haven't actually proven that it's stable, but again, it's just by intuition. So you know it's unstable here, so it makes sense that there's a stable, what you'd call a manifold, a stable solution between the two of them. But this is just a conjecture, okay? Now, if you want to show stability, you've also done this. I think on problem set 1 or problem set 2, how do you show stability? Well, you go and define a g equal to f of x. And then you have to go and check the gradient of g. And check, is the gradient of g, is it between -1 and 1 in this range of mu? All right. Okay, let's look at the cobweb diagrams. Let's look at the cobweb diagrams before we end this question. So again, on the MATLAB drive, hopefully some of you are using the MATLAB drive. If not, refer to the Moodle site to get you started. But now in lecture 11, I put in this little code here for the period doubling. So it's the same script as we've been using before. So we're going to go with two cases here. If I flip back to my my bifurcation diagram, I'm going to put in a value of mu. Let's call this point A here. We're going to put in a value of mu at this value, and then we're going to put in a value of mu at this value here, and see what happens to our cobweb diagrams, and see, could I have come to the conclusion that the bifurcation diagram looks like this without knowing very much, just by looking at the cobweb diagram. Okay, so let's firstly do the cobweb diagram for mu is equal to -1 on the left there. Okay, so you can see the function is inputted here. It's at -1 plus mu times x plus x cubed. And here, as you can see from the figure on the right here, you've got 3 fixed points. Okay, so you've got the one at the origin, and then you've got your x minus on the left here, and you've also got your x plus on the right here. Okay? Now again, look at the gradient of the function. The gradient is steep on the left here, so you're expecting it to be unstable. So if I click my mouse somewhere near the left fixed point, you should see it moving away from that fixed point. And indeed, it moves towards the center fixed point, where the gradient is shallow, right? It's less than, the magnitude is less than 1. And so it's stable. So you have unstable on the left, stable, and then unstable on the right as well. Again, steep on the right. So let's look at our bifurcation diagram. So at this -1, we have the left one. The left one is negative, so it lies down there. Unstable, stable, unstable. So in terms of what the motion that you saw before, the trajectory that you saw, let me flip back to the. Look at the cobweb diagrams, and you remember I clicked the button on the left here, and it moved towards the center fixed point. So in terms of the bifurcation diagram, that's like we clicked right there near the left with an x value of near the x value is the vertical axis, remember. So you click it near here, and then it moved towards the center fixed point. Okay? And then similarly, if I clicked it on the right here, it would move towards the center fixed point. Again, if I click on the right here, it would move towards the center fixed point. Okay? All right, so that's all fine and good. Let me stop this program now. And now let's investigate the case where mu is equal to 1. So if I now run it for mu is equal to 1, okay, you can see that I still have 2 fixed points. Okay? Let me, rather than mu is equal to 1, let me do mu is equal to 0.8, just so I get a little bit closer. I want those 2 fixed points to be a little bit more visible in the diagram. Not much more visible, but that's okay. All right, so again, look at the diagram here, and let's again examine the shape of the curve. So here you have a steep gradient as well, so you're expecting it to be unstable, except the one at the origin. You remember the one at the origin? This used to be quite flat. The solid curve at the origin used to be much more shallow. So at this point, you're expecting this red curve, it looks like it's just past the gradient of -1. And you're expecting this now to go to be unstable. And so if I click my mouse somewhere on the left here, it should certainly move away from the fixed point on the left. But then it can't move towards the fixed point at the center here because it's unstable at that. So it's going to end up jumping around, it looks like. Okay. Let's try again. There you go. So you see it's moved away from the left fixed point, moved towards the center, but then it's unstable from the center, so it has to move away from that. And again, it seems to move now towards the third fixed point, the rightmost fixed point, but again, that one's unstable, so it has to somehow wrap around. This is with n is equal to 5. If I increase this now to n is equal to 15, that's the number of iterations. You can see it starts to tend towards the 2 cycle. If I click it a little bit further away from the beginning of the 2 cycle, it also seems to tend towards the 2 cycle. Now, remember that we haven't made any proof about stability. It's not that clear that if I were to start, for example, where the mouse is at the moment, whether it does converge towards this 2 cycle, this box. Okay? It's just what we know from the analysis is that if you start near it, assuming the 2 cycle is stable, if I were to click, for example, here where the mouse is, then the chances are pretty good that you would eventually converge into that 2 cycle, as you can see. But the theory doesn't tell us the global stability. So if I were to click, for example, far away from the 2 cycle here, it's not clear that I would eventually converge to the 2 cycle. That requires a separate analysis. That requires more intense analysis. Okay. All right. Okay, now the last thing I want to mention, which I won't discuss right this moment, the last thing I want to mention is that you'll notice that this 2 cycle here looks like it fits within a box. Okay? Not only does it look like it fits within a box, it has to look like a box because it has to be a 2 cycle, but you'll notice that if I were to draw the line y is equal to minus x, so this dashed line is equal to y is equal to x. If I were to draw the line y is equal to minus x, actually the curve, the red solid curve, would intersect with the line y is equal to minus x. So there's actually a trick to figuring out the 2 cycles for odd functions, for functions that intersect in a symmetrical way with the line y is equal to minus x. And I'd like to talk about that on Friday. That turns out to be, that's something that's not in the notes, but it should be in the notes. We're going to talk about the fact that this looks like a box and the fact that it looks like the 2 cycle goes through the curve y is equal to minus x. This is the curve y is equal to x, the dashed line, but it looks like the curve actually goes through the line y is equal to minus x. And that's something that's going to be a trick to figuring out what the two cycles are for special functions, in particular odd functions. And this is a function that's odd. You can see because you have a power of 1 for the x here, and you have a power of 3 for the x here. And both of these are odd functions, and together that forms odd. Okay, let me flip back. All right, so that takes us essentially to the end. Let me flip to the notes here so you can follow along. Not chapter 7, but rather chapter 6. So that completes our analysis of this chapter. We've done the local analysis of this Taylor series. We've found the period doubling, the approximation of the period doubling bifurcation. My computer is being a bit slow, but it's right here, this square root function. And so that's why I meant that for this particular function, you could have figured out all these numbers here, just do a Taylor series expansion, just like you've done in one of the problem sets, and then figure out what the numbers are, and you put them in, and you'd end up with x plus or minus root mu. And we've done this example here of the supercritical pitchfork bifurcation. I haven't done the example where it's a subcritical pitchfork bifurcation, but it's essentially very, very similar. The only difference you'll see is a sign here. But the logic is still the same. Remember that it's supercritical. I've not written it in the diagram supercritical because I've got my two solid pitchfork arms flanking a dashed arm. Two solid here, whereas this one was subcritical. So this is supercritical. Super. And this is subcritical. Two dashed arms surrounding a solid versus two solid arms surrounding a dash. All right. Whew, that's enough for today. Thanks for listening. I'll see you on Friday.